Hello and welcome to Chapter 1, our first look at the vocabulary of statistics. Now, that may appear to be all that's going on when you read this chapter in the book, when you look through the workbook. As we go through this, I'm going to point out that what I'm teaching, what I am required to teach, is a classical statistics class. Now, I'm going to set up a simple distinction between a classical view of statistics and a Bayesian view of statistics. And I'm going to try to make it very clear where those two views of statistics diverge. Implicit in some of these seemingly innocuous definitions is a very significant philosophical difference between two schools of thought about statistics. So I'm going to point those out as we get to them. So as we go through this, there's a lot of boring stuff. You can read it. I'll be reading it to you. We'll get a lot of words dispatched quickly. I'm going to talk about ways to remember which each one is talking about and things of that nature. But as we do, I'm going to stop several places and I'm going to point out some implicit bias that is built in to these definitions that imply that we are teaching a classical statistics course. So I'm going to say those two words again so you can hear the difference. We're teaching a classical statistics class. You're in a classical statistics class. The more modern form of statistics is called Bayesian. That comes from the name Bayes. So as we go through, be on the lookout for that. Statistical basics. So here's a nice way to start. The mathematical path from data to knowledge. Lots of data out there, not as much knowledge. Throw in a little humanity and compassion and you may even get some wisdom. Statistics is the study of how to collect, organize, analyze, and interpret data. There are two branches. Descriptive statistics collects and organizes data. So collect and organize. Inferential statistics analyzes and interprets data. So some key terms. An individual is the person or object that you're interested in finding out information about. A variable, also known as the random variable, is the measurement, their height, their age, their preference in ice cream flavors, or observations of the individual, where how many of a particular last name exists in the telephone directory. A population is the set of all of the entire group of individuals about which we're interested. The population is usually the group, the set, that we're going to make a claim about. Now, it'd be fantastic if we could ask everyone in that population to tell us their favorite ice cream flavor or their height or their age, and then we could be sure that we didn't get a biased sample. But usually that doesn't happen. Every 10 years in the United States, we go through a process of taking a census. It is a huge undertaking, and it's one of the few times that we try to ask everyone about themselves. Generally, we only look at a sample. A sample is a subset. That's a very mathematical word. Basically, not the entire population, but a subgroup taken from within it. It looks like a population, but it contains less data. And the looks like is important there. It looks like a population because we've got a lot of data from our sample, but it may not be representative. So when we do something with the data that we collect from a population or a sample, we are calculating those numbers, whether they're means or standard deviations or something more sophisticated. A parameter is a number calculated from the population itself. So in other words, when the census is done, we'll know exactly how many people there are in the United States. That is a parameter taken from the entire population. This is usually denoted with a Greek letter. This number is a fixed, usually unknown number that you want to find in some way. As the semester goes on, we're going to make that idea more rigorous, how close we are to a true population parameter. Now, if we're looking at a sample, the number that we calculate from a sample is called a statistic. Now, these will follow us throughout the rest of the semester. These are good words to remember. They start with the same letter. The parameter is taken from the population, both start with P. The statistic is taken from the sample, both start with an S. Usually, statistics are denoted with letters from the Latin alphabet, so an X or an S, and you put a caret on it, that's a little upward pointing hat, or sometimes you just put a bar over it, X bar, with a dash-like creation over it. And since it's easy to find samples, statistics are readily known. There's lots of statistics out there. But of course, statistics change depending on the sample taken. Now, why do we do that then? Because they are an estimate of the true parameter's value. So let's now talk about the types of variables. So qualitative or categorical variables. So this is a name. It's a word that describes a quantity, or an individual. Quantitative or numerical variables is a number, something that can be counted or measured from the individual. So if it's a number, it's probably quantitative, unless it makes no sense to do arithmetic. Telephone numbers. I can't say someone's telephone number is bigger than someone else's. Street addresses are numbers, but it doesn't make any sense to do arithmetic with them. Now, when we have numerical variables, we may talk about the scale that's involved in those. So the least useful of these is nominal data. Now, this is just a name. It's basically falling into a particular category or another. There's no order to any of the data. I can't say that raspberry ice cream is bigger or smaller or in some way related to strawberry ice cream. There's no order to the data, and there are no numbers. You can't do arithmetic. So we might say genders, car makes, ethnicity, things that basically have been created from a sociological standpoint. The next is ordinal. Ordinal sounds like order, and it should. We're now able to put things in order. And I think you've all had an experience of this. Next, a good example of ordinal data is grades. Someone who gets an A and someone gets a B, that's a big difference on your transcripts, but it may not be that big a difference in terms of the actual score that the student earned at the end of the semester. At the end of the day, a 91% is not really that much different from an 89, but a 91 earns an A and an 89 earns a B. We can put them in order. We can say that someone who got an A did a better job in terms of demonstrating their knowledge than a person who got a B. But we can't really say how much better that knowledge is. We can't really comment on the actual magnitude of that difference. So there is a way of putting them in order, but you can't do arithmetic, even though we could say first, second, third, small, medium, large. You still can't subtract and say, well, the third place is a third as good as the first. The third place may be almost identical to the first, just a skosh less than second place. So we can put them in order, but we can't do arithmetic. Now, finally, we can do arithmetic with the last two. So if data is in interval form, it's ordinal. In other words, you can put it in order, but you can now do arithmetic with it. You can subtract. And you can say that if it's 4 o'clock now, and an hour later is 5 o'clock. They're in order, and you can say what that difference means. So temperature, you could say that the temperature increased by 5 degrees. Time passing, you can say that it's now an hour later. The most useful data comes to us as a ratio. That is data that is ordinal and interval, but now you can also do division on it. You can say that one data point is twice as large, or 30% more, or 15% less than another. So now we can start to do all of arithmetic with this level of data. So height, because it has a true zero, weight because it has a true 0, distance because it has a true 0. And now notice that time is back. In the previous example I said time on a clock. Now I probably should have said here time on a stopwatch. If I run a race and it takes me 15 minutes, and you run it and it takes you 7.5 minutes, it took me twice as long as it took you. And the reason is because both of those have a true 0. So be very clear that time can be kind of a silly thing. It can be on a clock, in which case 5 o'clock is not half of 10 o'clock. That arithmetic doesn't work, but time could just as easily be on a stopwatch. In other words, having a true 0. Now what about temperature? If we talk about interval data, an example that I gave of it was temperature, and certainly I can say that 85 degrees is 5 degrees more than 80 degrees. But I can't say that 80 degrees has twice as much energy in it than 40 degrees. And that's because when we talk generically about temperature and we simply say degrees, we probably mean Fahrenheit, or if we were in much of the world, centigrade. Neither of those have a true 0, though. In other words, 0 degrees Fahrenheit is not the temperature when all energy in matter stops. So you might say, could you have temperature data that is ratio? And you could. So this is an aside just to make this distinction about having a useful 0 and how important that is to distinguish that you have ratio data. There is a temperature scale that has a true 0, and it's called Kelvin. 0 degrees Kelvin is actually the temperature at which all motion stops in matter. It's more theoretical than anything. You can get really close to it, but it's kind of a philosophical question at some extent. But it's designed so that you can say that 40 degrees Kelvin, and I don't know what that means, is half as hot as 80 degrees Kelvin. In other words, that's a scale for temperature that has a true 0. Now, I'm not going to play that trick with you. I only mention degrees Kelvin to point out that you can make temperature into ratio data, but you have to be really careful on how you do it. So if you see temperature, if you see clock times with the 2 dots above each other, you know you're talking about interval data. If you're given time as a stopwatch, it took someone 5 hours, someone else 3 hours, then you're thinking of ratio data. Height, because there's a true 0, weight, distance, and time for the same reason. Let's talk a little bit about numbers. So counting numbers, the integers, the whole numbers, the natural numbers, and then of course measuring numbers, fractions, decimals, and scientific notation. So sampling methods. Sampling methods are when we're out there trying to collect data. If we collect everything, if we try to measure everyone, then we're performing a census. It's expensive, it takes a ton of work, and even then there are issues. But it's good to have rock-solid foundational data for as much as you can. So if you've got a census, you're great. So it's not really a sample, is it? Because a sample, remember, is a subset of the population. If you're measuring everything, a census is really a parameter. The simple random sample. So this is a way of teaching statistics at this level and implying the existence of a way to make a good sample. So what do I mean by this? If we know that we have a simple random sample, then every different possible sample of whatever that size is has an equal chance of being selected. So you have as much chance of being included in the sample as someone else. Simple random sample, by the middle of the semester, we'll start abbreviating this as SRS. It's a nice way to say someone else is dealing with the intricacy of performing the sample, and they did what in classical statistics is considered a good job, and so we'll just go with it. An equal probability for each possible sample. Then we've got a simple random sample. A stratified sample. So we divide, and that just means break into groups. we divide the population into strata. That might be age group, it might be state, it might be whether they have a landline or not. And we randomly select in each of those strata. That ensures that we're getting a random sample, but that random sample isn't really that random. In other words, we're going to go after a random collection each of these stratas. So systematic means that every nth, if we're looking at the production off of a factory floor, we say let's sample every 120th washing machine that comes off the factory line. So the 120th, the next 240th, you get the idea, and we sample those. So we're assuming that we're going to get a systematic sample by getting every nth one. Cluster samples are a little bit more interesting. We divide the population into clusters, and then we do something interesting. So imagine that these clusters are much smaller than what I was illustrating for the stratified sample. So if you're talking about the United States, then the clusters may be certain post offices, relatively small clusters. So we then randomly select clusters, and then we sample all, generally, in those selected clusters. So this is very different from stratified. Cluster sampling is very different from stratified sampling. In cluster sampling, you basically choose a way of dividing the population up into these clusters, and then you choose randomly some of those clusters to sample. Remember, in a stratified sample, our goal is to make sure that we get at least a representative amount from each strata. So we divide it up, and then we randomly select within each one. And then finally is a convenience sample. This is just saying, hey, do you have a few seconds to talk to me? And so you'll basically get people who don't mind talking. You'll get extroverts. You'll get people who maybe don't have to be anywhere at any particular time and wouldn't mind talking with someone. It's not statistically valid. Perfect example of this is call-in talk shows, where first off, to even know to call in, you have to be listening, so you're already of a particular group. And then someone decides whether you get to go on air or not. There is no statistical validity in a convenience sample. Now, bias is a word in psychology. It's also a word in statistics. We can refer to a person being biased, but in this case, we're referring to a sample being biased. Now, this bias does not necessarily mean that it favors one group or another. It simply means that the sample does not represent the population from which it was drawn. So the key here is that it does not represent the population. So it may be a simple random sample. It may have been a cluster sample. We may have done a bunch of things, but randomness could come into play and cause it to not represent the population. So bias in this statistical use of the word does not necessarily mean that we have made a mistake, that we are in some way to blame for it. Now, that doesn't mean it's not bad. It certainly means that we have useless information. It does not represent the population from which it was drawn. So, what do? So if we try to draw conclusions from a biased sample, it's not going to apply to the population. So how do we avoid it? We may be able to say, it's going to be hard to sample this group of people. It may be easy to sample people with landlines. It may be easy to sample people who, ride the bus. It may be really hard to sample folks who don't have a landline, who aren't out in the public space. So in that case, we may anticipate that some people are hard to reach, and we may maybe make a strata where we spend a lot more money trying to reach a randomly selected group of people within that strata. So maybe we anticipate bias. We think about sources of bias. We think about how samples may select for certain responses. We think about these things and we try to overcome them. In other words, bias is kind of a challenge to us. How do we actually make a sample that is representative? And in classical statistics, what we say is we want randomization. We want a random selection of people. And that's the best way to avoid bias. And we'll see why, arithmetically, that is a good way of doing things. We'll actually talk about, later in the semester, we'll talk about the size of a sample that we need so that those random fluctuations in who we get kind of cancel each other out. So the next question is, how do we design an experiment? There's different kinds of experiments. So an observational experiment. So we're collecting data merely by watching or asking questions. So we observe people, hence an observational study. We ask them questions, but we're not changing anything. We're not asking them questions and then showing them a video or going back a year later after something else has happened and asked what's happened. This is basically one shot at asking these questions. Now, an experiment is very different. Here we are going to change a variable or impose a treatment. And a treatment is a weird statistical word to say that we did something. So a treatment could be a pill, a treatment could be reading something, a treatment could be watching an advertisement and then asking how a individual felt about a political candidate before and after watching that advertisement. Now, an experiment is the first glance that we have at a distinction between classical statistics and Bayesian statistics. Notice that in the definition in classical statistics of an observational study, there isn't a discussion of using statistical methods to make that observational data represent a population. And that can be done, sometimes very easily. So already in this chapter, and we're only on page 3, we're seeing some of the philosophical differences between classical statistics and Bayesian statistics. Remember, I'm asking you to learn classical statistics. Personally, I believe that Bayesian statistics makes much more sense. It has much more power. It has much more subtlety to it, ability to overcome problems. But here's our first look at this. Experiments and their role in making statistics work for us. So how do we design an experiment? So I'm going to go through this very quickly. As you can see, I don't have any boxes here. So we're going to identify who we're interested in. We're going to specify what that variable is, what it is that we're measuring about them. What population did they come from? Fourth, we're going to look for a way of figuring that out. How are we going to measure it? How are we going to get a sample? How are we going to actually collect that data? What can we use that data to tell us? And then, to kind of close the loop, what were the problems? What biases did we encounter? What issues do we need to use for the future? Here's where classical starts to come into stark relief with Bayesian. An observational study, the investigator collects data merely by watching or asking questions. They don't change anything. And I would definitely agree with that. But this next sentence is pure classical statistics. A classical statistician will say that it is therefore very hard to establish a cause and effect relationship through an observational study. Personally, I do not believe this. I believe very strongly that you can use observational studies to make very strong claims about cause and effect relationships. Experiments. So the role of an experiment in a classical statistics class is that the investigator makes a change, does some treatment, and determines its effect. Now, that in a classical statistics setting is how you establish cause and effect. In a classical statistics setting, it is the only way to establish cause and effect. So let's talk about this in two ways. One in a very kind of emotional setting of lung cancer, and one in a very perhaps dry setting of the role of mathematics in data analysis. If you are a classical statistician, and there are fewer and fewer of these, you would say that we did not know that science, that math, that medicine did not know that smoking caused lung cancer until the 1980s. If, however, you are a Bayesian statistician, you would not say the 1980s or the 1970s or the 1960s. You'd actually say the mid-1950s. And that is a huge difference. If you know something early, if you can know something causes a debilitating and horrible disease like lung cancer, you want to know that early. You want to know that late, however, if you are making tobacco products, if you're selling tobacco products. So you can see already that there is a very, very strong distinction between classical statistics that generally works to reinforce the beliefs of the status quo, and Bayesian statistics that very much seeks to justify change. If you knew in 1955, and of course by this I mean someone in your family, a parent or a grandparent, if you knew in 1955 that smoking caused lung cancer, it's a horrible disease, and that was communicated in that way, think of the number of people who would use that data. Now, the reason that 1955 is used as this kind of Bayesian hard date for knowing that smoking caused lung cancer is because that is when the tobacco industry actually put an advertisement in major American newspapers saying the very same thing. It was established through observational studies. There were no experiments. Now, I'm going to drill this a little bit further home, so kind of a trigger alert about animal testing. Observational studies do not require experiments. I mean, that's what this section says, right? You look at the number of people in the hospital who have an ashtray next to their bed, and in the 1950s, you could smoke in a hospital. So it's easy to collect that data. Now let's compare that to an experimental study about smoking and lung cancer. We're not simply going through hospitals, noting the disease and noting whether there's an ashtray next to the bed, something you could do really easily in the 1950s and was done. Instead, you'd have to strap and lock and do nasty things to animals and force them to breathe cigarette smoke and just terrible, horrible things. And that would qualify as an experiment to show cause and effect. So you can see that there is a very strong philosophical difference between these two schools of thought. What I'm asking you to believe about classical statistics and what will be on exams is the claim that the only way to establish cause and effect, that something causes something else, is to perform an experiment. Okay, so let's talk about how we can perform an experiment. So there's randomized two-treatment experiments. So we have a placebo and a control group. The control group is the group that we do not perform the experiment on. Now, if this is human beings, we might give them a placebo. A placebo might be a pill that looks exactly like the pill that we give to other patients who are not in the control group. It might be the same color. It might come in the same box. It might even make the person who signs it out go through the same security protocols as if they were giving the real pill. So a placebo is meant to look and smell and sound and feel and have all the characteristics of being in the treatment group. But of course, the control group is just getting the placebo. When psychology isn't an issue, when you can simply say you're testing the flow of some pipes, you don't have to worry about a placebo. You can simply say, well, this amount of water went through at this amount of time and that amount of water went through at another time. So a randomized block design we take subjects that are very similar, but the blocks differ from each other. Then we randomly assign treatments to subjects inside of each block. This may seem a lot like a stratified sample to you. Rigorously controlled design. This is when we do not rely on chance alone to make our sample, but we carefully look at those folks that we want to be in the treatment group, and we base our results on that. If we are making a claim about a certain population, we want to be very careful to select individuals that come from that population. And of course, that means that it is important to the experiment that each of those are treated in a similar way. So, matched pair design, the treatments are given to two groups that can be matched or paired up with each other in some way. This doesn't have to be even two groups of individuals. Certainly twins work if you're looking at something like genetics or other factors. It could be something as simple as your left hand and your right hand. That's definitely a matched pair. For each right hand, most people have another hand. What do we want to be able to say about an experiment? We need the experiment to be repeatable, to be replicatable. So to do that, we need the study to probably be performed many times. No one's going to do anything based on a single study. Another university is going to do it. They're going to go out and see what happens in Indianapolis and compare that with Sacramento. Now, blinding is an interesting idea. I got into this a little bit earlier when I was talking about placebos. So single-blinded means that the subject does not know if they are in the treatment group or in the control group. So let's change that. So what that basically means is they don't know whether they're getting the placebo or the real pill. Double-blinded is interesting for significant reasons. In a double-blinded experiment, the experimenters themselves do not know whether they are interacting with someone in the treatment group or the control group. And that's critical, because if I know that I've got a placebo that costs 5 cents, I may not even, I may put it in my pocket, I may not even worry about it, right? If I know that I've got an experimental treatment that costs thousands of dollars to make, I've signed it out, I may be perspiring, I'm holding it, I can telegraph to the subject whether it's a placebo or the real treatment. So in a double-blinded experiment, I don't even know. Did I sign out a placebo? I had to use my pass, I had to sign it out, or did I sign out the real thing? I don't know. So I can't telegraph that to the subject. So let's talk about time. There's 3 groups here. So cross-section, we divide up the data, we measure it, and we collect it all at one time. So we look at one point in time, and we get all of our data from that one point in time. Retrospective is a study that looks at the past. So we're looking at data that was already collected and put into records, or already collected and put into interviews, or some other similar artifact. In other words, something looking backwards in time. So the thing's already happened, and now we're collecting data about the past to use that past information to make a claim about the future. Prospective studies is data that looks to the future. So basically, if I say, okay, I'm going to look at what happens in the future. I'm going to select some folks, I'm going to talk to them, I'm going to say, write down your daily behavior or something of that nature. They are then going to perform that study into the future. So prospective, looking into the future; retrospective, looking into the past; cross-sectional, looking at one point in time. One of the biggest differences. There's going to be three, and I will summarize these differences between classical and Bayesian statistics before we end. But one of the biggest differences is the role of a lurking or a confounding variable in classical statistics. The idea here is that you can show that one thing is very highly correlated to another, but that does not show that one thing causes another. There may be something else. So when you cannot rule out the possibility that the observed effect is due to some other variable rather than the factor being studied. So I'm going to give you the canonical example of a lurking or a confounding variable. So it happens to be the case, and this is a true statement, that as ice cream sales go up, so do the number of people who die by drowning. Now you might say this is terrible. Clearly, something about ice cream is causing people to drown. I mean, maybe they're drowning in ice cream. The lurking or confounding variable, of course, is that for most of the country, when the temperature goes up, the amount of ice cream that people consume increases, and of course people spend more time outside at rivers and in swimming pools, and those activities are correlated to, of course, drowning. So, does ice cream cause drowning? No. They are correlated, they happen at the same time, but both of them have the same other variable that is causing them to increase together. So, the temperature goes up, ice cream consumption goes up, and drowning goes up with it. We cannot say that ice cream causes drowning. We can say that summer is correlated with drowning and eating more ice cream. So a lurking or a confounding variable is a way of basically saying that unless you perform an experiment, you cannot say that just because things are correlated, one causes the other. Okay, an overgeneralization, you do a study on one group, that is one population, and then you say, hey, that'll happen to some completely different population. Or maybe even make the claim that it'll happen to all groups, all of the other populations. So that's an overgeneralization. If you talk to high school students and you say, well, that represents college students, well, that's not the way it goes. There are different populations and they behave differently. So cause and effect. Cause and effect is something that it would be very, very nice to use statistics to tell us. It would be great for someone to tell us what causes heart disease and things of these natures. In classical statistics, we cannot say that one variable causes the other just because the variables are related or correlated. So if that looks to you like the same word with a C-O-R plugged in front of it, it is. Related, correlated, same root, same idea. In other words, drownings and ice cream consumption go up at the same time. They're correlated. So we should be very clear to have a word that says they happen together, but that one doesn't necessarily cause the other. Eating ice cream doesn't cause you to go drown. So as a result, it's very difficult to establish cause and effect from observation alone. And this is the key sentence that distinguishes that we are in a classical statistics course. This basically says that you've got to do an experiment. If you want to talk about cause and effect, refer to the previous page, you've got to do an experiment. There is no other way out of this. There is no way that an observational study can show cause and effect. Notice that we now say very difficult in a classical setting. A Bayesian statistician would not say that. But of course, some would say that a Bayesian statistician relies on experiments that were done or population data that was collected at some other time. So this is a classical statistics statement. Okay, other issues. Sampling error. There's a difference between the sample results and the true population results. We'll call that sampling error. That's a kind of bias. Non-sampling error. That's because we made a sample that was poorly designed. Either there was too much bias built into the sample, or there was an error in the measurements. And of course, this is our problem. If we did not design the sample well enough, then we have non-sampling error. If we have sampling error, that's also bias, but that could come simply from the fact that we used a random sample, and randomness may have meant that we oversampled certain parts of the population at the expense of others. So in a classical statistics setting, sampling error is something that we kind of sweep under the carpet and call an artifact of randomness, but we do acknowledge that non-sampling error is our fault. We need to be able to make samples that have good measurement designs and collect a fair cross-section of the population. Now, something that you could spend an entire course talking about and maybe even kind of break into the realm of philosophy is the meaning of results from statistics. If I say statistically that a new drug reduces the instance of a terrible disease, and you say that's great, but the drug costs a fortune and it only increases it a little bit, well, okay, then maybe it's not that significant. So we have to distinguish statistical significance from practical or clinical significance. So what is statistical significance? We say that something has statistical significance if the results are not due to chance alone, to the random sampling technique. Throughout the semester, we're going to say a simple random sample was performed. Or maybe we'll go to a respectable outfit that does samples and we'll assume that they did a good job. So in a situation like that, we'll say that there is statistical significance. In other words, the results probably represent the population, and of course probably is the key word there. But there is a huge difference between that and clinical significance. If I show that something does a great job, but it's at the expense of something else, like being very expensive or providing the other organs with too much stress, then maybe I haven't done that much in a real world setting. Does the effect really matter? I can say with very high precision in some instances that some treatment results in good. That's true in that situation, but it may not be enough good. It might be a tiny change in the number of people who suffer from a specific ailment. Okay, let's look at surveys and how bias can be built into them. The wording of a question can cause hidden bias when the questions are asked in a way that makes a person respond a certain way. And I'll post a link to a video that makes that pretty clear. So non-response, you send out a survey, but not everyone returns it. So we've not captured everyone. Voluntary response. So people are asked to respond in a particular way. The problem is that only people who really care about the topic are likely to choose to respond. Okay, so let's quickly wrap up the distinction between Bayesian and classical statistics. A Bayesian statistician would say that we knew that lung cancer was caused by smoking, or I should say correctly, that smoking caused lung cancer in 1955. A classical statistician would have waited until hundreds, if not thousands, of experiments were performed on animals, and lots of people died from smoking in 1980 to make that claim. Another way of distinguishing classical from Bayesian statistics. Classical statistics generally relies on arithmetic. If you introduce algebra into statistics, you get Bayesian statistics. In a classical statistics setting, this is key, this is terribly important, you have to say three things when the word causes appears. If someone calls you up and says, I know you're a statistician, tell me if this causes that. A classical statistician says the following: correlation does not show causation. The second thing is, there may be a lurking variable. And the third thing is, an experiment must be performed to show cause. So those three things distinguish the response of a classical statistician to a question of cause. And that ends chapter 1. You can now take the quiz that gets you into the homework, so enjoy.